All right, good afternoon. Yeah, welcome to the Research and Technology Forum. This is a monthly activities. We try to get industry and faculty researchers together and to have some discussions. And today I'm very pleased to have two faculty members from Environmental Science and Forestry, SUNY ESF, to give a talk on the drone-based techniques for building assessment. You know, COE works on air, water quality, and energy, renewable energy, but we focus a lot on buildings, right? Buildings and communities. So the first step is actually do a good building assessment and then see what kind of improvement we can have. So I think that today's talk is very timely. Look at what kind of techniques can be used to quickly assess the building conditions and suggest the retrofitting. So just quickly, the speaker today will be Professor Paul Crovella, and he's an associate professor of construction management, and he has done a lot of interdisciplinary research. I think the focusing on timber construction, timber-based constructions, and you can see his CVs here. But I remember very vividly he is the president or chairman of the Green Building Conference last year, and that was a focus on timber constructions, and very nice conference. So I think he's very well known in this area. And then the second speaker is Shayan Mirzabeigi, and he already has a PhD in construction management, but he felt it's not enough. He needs a second PhD, so he's getting so he's working on another PhD in mechanical and aerospace engineering. Again, I think he's also very interdisciplinary researcher. Construction management, architecture. He got 3 degrees. One is from Iran University of Science and Technology in Iran, bachelor's on architecture, engineering, and then the energy system is from MS from Italy, Polytechnic University of Italy, and already a PhD from ESF on construction management. So 3 different degrees from 3 different places and 3 different disciplines, right? So he's working on another one. So I guess without further ado, I will let the speakers introduce themselves and give the talk. Yeah, let's welcome them. Yeah.
Thank you very much, Jensen, for that wonderful introduction. And thank you all for being here today. Very excited to be able to share the work that Shayan has been working on for a number of years. And actually, as Dr. Zhang explained, he's continuing to work in this general field of understanding how we can build better buildings and how we can improve the efficiency of the buildings that are out there. So very pleased to have him aboard. Although we're listed as co-presenters here, that's really not exactly the situation. So my role in this was as follows. Shayan came aboard back in 2000 to ESF, to 2020. Yep. So arrived in 2020, midst of COVID, all of that was going on, was actually working with a different faculty member. That faculty member moved on. And so I moved into a role of supervising Shayan for the PhD that he completed at ESF. In that position, there had been a grant written, and with the wonderful support from the Center of Excellence, we were able actually to get funding to do this work. So this work really came about because of the efforts that were put in getting that grant and the support from the COE. So let me just recognize that and say thank you for that. And so Shane comes into my office. We talk about this proposal, and from that point on, while we collaborated, Shane really did a lot of independent and very creative work in planning his path forward, plotting it out, and going and making sure that he had enough sort of sounding boards to make sure that the direction he was moving in was correct. So again, as though we're listed as co-presenters, today will be Shayan's day, okay? And I just want to sort of thank the Center of Excellence again for making this all possible, because if that sounded a little bit complicated, what went on, there was a lot of paperwork and bureaucracy, and the Center of Excellence was very patient throughout that process to get us to where we are. So,
thank you. I think I'll just take the main part. All right. Thanks, Dr. Zhang and Dr. Crovella. So I would like to also thank Center of Excellence and the support that we received from this center, as well as the director, Professor Jensen Zhang, for successfully delivering this project. So the project is really an initial step for understanding the potential of using drone-based technology for building assessment. So during the time that I was working on this project, I was working as a research assistant and was a PhD student. And the majority of work was also related to my PhD dissertation in construction management, which was focused on assessment of the existing buildings and trying to understand the potential of using drone-based technique for building envelope assessment. So with that, I just wanted to note that this is just the beginning of trying to explore the potential of using this technology for us. And there are a lot of opportunities that I'm going to just mention at the end of the presentation and just open the eyes for future research and development for future projects. So with that, I would like to start explaining a little bit about the background for the emission of the building sector. So in general, we know that the building sector is a significant contributor to global emissions worldwide. So in addition to energy consumption, it's important to take consideration about greenhouse gas emissions. So in particular, we see the buildings can be represented as subsectors of residential and commercial. So we see residential buildings represent 22% and commercial represent 19% of these emissions in total. So in general, there are about 40% that is represented by the building sector. So in New York State, in general, to address the clean climate goals, by 2030, there is a clean climate target in order to reduce the total emission by 80%. And by 2050, there's a goal to achieve zero emission sector. This is very important. I just want to just try to highlight this so that you understand the importance of trying to be innovative and use technological approaches for building assessments. And as Professor Zhang said, building assessment is really important. So this center in particular is focused on the intersection of air, energy, and water. And buildings, as I said, are one of the main contributors that play an important role in these three disciplines. So in particular for the building assessment, the initial process to characterize the existing condition called energy auditing. So the traditional way that we do energy auditing to understand the existing condition and to assess the saving potential for various energy conservation measure scenario is really time consuming. Sometimes, depending on the case studies, it might be also not necessarily scalable. And sometimes, depending on the size of the building that we're working with, might also associated with safety challenges. So that being said, and by considering the potential of reducing the emission from the building sector, this research is really focused on existing building assessment. In particular, we are focused on building enclosure or building envelope. So building envelope, the term that we refer to as building envelope, is essentially a separator between indoor and outdoor environment. So apart from having the function of finishing and having the main function as the aesthetic of the building, it's a main control layer that regulates the thermal loads in building. So based on US Department of Energy, opaque buildings and opaque related energy use is accounted for about 28% of total building energy use. And retrofitting the existing inefficient envelope represent a good solution, scalable solution to reduce energy use and to reduce the cost as well as carbon over time. Apart from these main benefits, there are also co-benefits for improving thermal comfort, health, and well-being for the occupants. So with that, focusing on energy retrofitting, design, and fabrication of the energy retrofit, there are various barriers and challenges. The reason is when we focus on an existing building that is not efficient, the first thing we need to do is to capture the existing data. So usually because of the structure and because of not availability of the data, capturing this information is relatively complicated. There are uncertainty for capturing existing building data. There are also other aspects that kind of relates to the scope of this assessment about space congestion. For instance, if you would like to do an integrated envelope, the space and the use of space, specifically talking about interior space, is another limitation. So for that reason, we see more recent solutions for integrated envelope retrofitting is more focused on adding layer of insulation to the exterior of the building envelope. Time is also one of the other main concerns that many of the energy retrofitting are being challenged by. So by reference to the US Department of Energy report about potential for improving envelope diagnostics, for improving the building emission, we see there are two main targets that are being addressed. So the first target is time, and the second is cost. So in terms of the diagnostic for the opaque envelope, by averaging the existing approaches, the time metric is 10 seconds per square feet, and the cost is $200 to $500 per test. But what DOE thinks about we should target by 2040 is we should reduce the time to 1 second per square feet and the cost to average of $100 per test. So this contextual information is important because using drone help us to improve the speed of data collection, but there are also considerations that we are going to talk about in detail in this presentation. So the next thing I would like to address here is using drone is not something new. Other researchers and other studies have used drones for and drone-based approaches for different purposes. So this figure tries to summarize the information from survey with different companies, construction firms, and the firms that focus on building performance. So you see different categories of the use case of drones for built environment application. More important, those that are highlighted are those categories that are more related to building enclosure integrated assessment. In terms of use of the sensing modules, high resolution camera, LiDAR, and thermal sensors are the technologies that are being integrated with the drones for data collection purposes. And here you see examples of some of the categories. For instance, the first image here shows an example of visual inspection from a breach case, which for structural assessment purposes. use of drone for as-built documentation, construction sequence monitoring, as well as as-built documentation is something drone is being used for, 3D modeling, and also for purpose of thermal and thermography of the existing building condition, drone is being commonly used. So a little bit of context information for some of you that are not very familiar with categorizing the 3D as well as layer of information in a form called building information modeling. So building information modeling is a digital representation of the building that records layer of information. So this image here shows examples of category of different information that relates to different life cycle phases of buildings, starting from construction to demolition. This is important, again, thinking back about the initial slide, thinking about how we can address the challenges, how we can improve the existing assessment technique. Building information model is a technological approach that can be used. The reason is in order to assess the existing condition for majority of the inefficient building in the United States, there is no as-built documentation. So for that reason, proposing approaches that can automatically capture a different layer of information as well as geometric information is super helpful and help to address reduction of the time aspect for building assessment. In terms of the categories of beam, we usually have as design and as built beam configuration. So something we are focusing here is as built, and as built is being used for detection of defects, for quality control. It also helps to support decision making as well as make decisions throughout the operation as well as for maintenance of the buildings. So the main question here is how to sense and represent the physical environment. So in different beam models and beam tools, a 3D scan point cloud is used as a guidance that helps modelers to effectively capture the geometrical information. So the traditional approach for capturing this information is using laser scan. So on the right, you see an example of using a laser scanner in order to capture the 3D point cloud data. And related to our approach, however, is the use case of image-based technique and applying photogrammetry approaches in order to recreate and reconstruct the 3D point cloud using the combination of image data sets. So one of the main questions we wanted to answer here is, can the 3D point cloud that reconstructed from a drone-based approach represent a target level of accuracy compared to laser scan data in order to be used for retrofit design as well as fabrication purposes? So here, this graph shows the overall workflow of a drone-based approach that we propose as part of the study. So throughout the different part of the presentation, I'm going to focus on different aspects of the workflow, but in general, we start from the existing building. So this is with an assumption that we have already selected an existing building that is an efficient. We would like to do a building assessment. We would like to reconstruct the beam model. We would like to understand the different sections of the building enclosure that might represent a potential for controlling additional heat losses to improve areas of inefficiency or thermal inefficiency in the beam enclosure. So there are different steps involved in this workflow. The first step is data collection and analysis. So the data collection and analysis is being shown by the blue color. So after selecting the reality capture approach, in this specific case, we are essentially focused on a drone-based approach. We use two types of data: visual data, which is essentially a collection of RGB images, as well as thermal data. So these two main type of data gives us as a main input, and then applying the photogrammetry approach, we try to reconstruct the point cloud, create the beam model, and then develop an existing energy model in order to understand the baseline energy model for the existing building. There are other potential of using thermal data to apply quantitative as well as quantitative thermal characterization. Example of quantitative is R-value estimation. Example of qualitative is thermal anomaly detection, to understand which portion of the envelope represent areas of thermal losses. The pink color here also represents another step, which is initial modeling. Initial modeling use third-party data set in order to train a semantic segmentation model, and to use the trained model in order to separate the information from the point cloud. And this separation is focused to essentially classify the point cloud into different components, including wall, windows, doors, PV panels, and roof as part of the enclosure. And then post-process this information to be able to represent different components as the main part of the building enclosure in the BIM model. These information are used as the main input for the third step. So the third step here is retrofit design. So retrofit design is usually needs a lot of interaction with the architects and the design team. And after implementation, we see the fourth step of the workflow, which is performance verification. So the same approach not only can be used for assessment of the existing condition, also after applying the retrofit scenario, we can use it to verify specific performance aspects. Okay, so we are diving a little bit deeper into specific aspects of data collection and applying drone-based technique. So the first case study is the data collection for a building called Building Envelope Test Laboratory. So Building Envelope Test Laboratory is an example of a single-family residential building and is being used for assessing and analyzing different type of building envelope systems. So the building is located on Syracuse University South Campus, and for specific purpose of data collection, we designed two different type of flight path. So on the left here, you see a rectangular flight path. On the middle image, you see elliptical flight path. And we did a detailed literature review to understand what is the potential of using different flight path design for a specific purpose of drone-based data collection and also processing and characterization. So rectangular flight path is usually being used for the cases where you need a high level of overlap between images and you need a high resolution for data analysis. And that example, for instance, represents a thermal anomaly detection that I'm going to show example of. The second flight path is elliptical flight path. So elliptical flight path essentially is a circular flight path. It's relatively quicker, so we can easily capture the data. So for this specific case study, we designed elliptical flight path at three different elevations, 18 meter, 24, and 30 meter, and compared the results from different flight path data collection to compare the output of 3D point cloud reconstruction. On the right, you see a real example of actual flight path being represented on top of the initial high point that was created as the initial step of 3D point cloud reconstruction. And this workflow shows an example of a detailed approach for representation of how we can use an initial input image data set and come up with a 3D point cloud using a drone-based approach. I don't want to get into the detail of photogrammetric approach, But in particular, we used a software called Pix 4D Capture here for collecting the data, and Pix 4D Mapper to adjust the photogrammetry approach and parameter that we needed. For instance, the level of the density for dense matching setup as part of the photogrammetry step for reconstruction of the point cloud. Once we recreated the point cloud here is the output of point cloud reconstruction. We apply a segmentation. So we separated a reconstructed building scene into different classes. In particular, here we applied building class, vegetation, ground, and handmade objects. So the purpose was apply classification and then separate the class of building, because we wanted to use as an input for another software called Recap for geometrical modeling and representation of the actual geometry in the form of beam objects. And then the geometry was used as an input in the form of 3D model in another energy modeling software called Energy Plus. So probably many of you have heard about Energy Plus, which is a DOE developed energy modeling software. So this is the example of different scenarios that I mentioned. So the computational time and the number of points have been represented. So starting from scenario 1, we see the results of the point cloud reconstructed from the scenario with lowest elevation. So it is obvious that the scenario 1 represented the optimal scenario in terms of the elevation. For this specific case, which can be considered as a representation of single-family residential building. And then in another step, we applied classification. So we separated the classes inside the point cloud 3D data. Then, as you have seen in the classification, the results of classification was not very high level in terms of characterization of different components and different points. So we applied another step, essentially a parameter tuning step. So we came back and applied some tuning optimization of specific parameters used in the dense matching. So, and then we see the results of point cloud that reconstructed here is much better representation of the actual condition of the building. But another thing I want to focus here is the difference between the computational time, the number of points here between scenario 1 and the parameter tuned scenario. So we see a much significant difference between the computational time for the processing of the information here. Then, as I said, one of the main questions we wanted to answer here was assessing and validating the accuracy or relative accuracy of the drone-based 3D point cloud. So we collected the data using a laser scanner from the same building and used the laser scanner data as ground truth data. So we applied cloud-to-cloud difference mapping approach to essentially try to characterize the average level of deviation between the 3D point cloud data reconstructed from drone-based approach versus the laser scanning approach. So this, the first graph on the left, top left showed the laser scanner point cloud, and on the right showed the deviation map between the first scenario and the laser scanner scenario. The second image here shows the same comparison between the parameter tuned reconstructed point cloud versus the laser scanner. So the comparison between the error deviation fitting showed a much better results. And you see from the deviation map, you see a much lower level of error. So in general, try to summarize this information. Doing this initial exploration and research, we were able to achieve a metric of what's called level of accuracy of 20. So for exterior retrofitting And for the purpose of characterizing the level of error, the level of accuracy is commonly used. So 30, 20, 20, 30, and 40 are the common level of this metric that is needed for the fabrication of reality capture from the existing condition. So that's the results from this step. Okay. And then we, as I said, we apply the framework. We essentially import the reconstructed geometrical information into the energy model, and we were able to successfully run and debug the developed energy plus model. And you see some of the like primary baseline energy data we were able to show for the baseline best test case scenario. For some of the previous step of the workflow, there were semi-automated connection. So moving from one step to another, we had to manually take the output from a software and then use the output as a form of input to another software. So for that reason, we try to come up with an approach which is more integrated and try to give us a better level of automation. So here you see in general, a general structure of neural network architecture. So essentially, using neural network architecture helped us to essentially get a form of 2D or 3D input data, apply layers of convolution and max pooling in order to be able to separate different points in a point cloud and segment those as specific classes in an experimental case study. So the particular architectural form that we use is what's called the PointNet framework. So PointNet essentially consists of pointwise convolution layer and apply these convolution layers and max pooling over the whole 3D point cloud target domain. So in terms of the data that we use for this experiment, we use an open source data from what's called a Stanford dataset. You see example of import of the point cloud, and then the results of the segmentation. Here shows some of the examples, more detail from the scene. On the left, you see example of the visualization of the training data. And then on the right, we see the example of the prediction from the application of this neural network in order to be able to separate different layer of semantic information available in the enclosure 3D point cloud data. And then relative accuracy and precision of the results reported here. So we tried to experiment the application of neural network because the ultimate plan was to integrate different steps. So here shows the example of data collection, segmentation, fitting, and relationship detection in order to automatically characterize different parameters, including the geometry, orientation, thickness, location, in order to characterize a specific object. In this specific example, we apply the framework only for the wall detection object for beam classification. And then use this information as an input. Everything is integrated on a software called Grasshopper, which is a parametric interface in the Rhino. And then the output from the beam characterization as the geometry in the form of wall object used as an input in another software called Honeybee. And the Honeybee used the, similar to the previous case, used the already validated energy plus simulation engine for setting up the energy node. So we have already seen the example of being able to recreate the building model and use this building model as an input to set up the energy simulation model, and to validate the results from creating these models from the geometrical representation approach. But the next part of the framework that we are focused is more, so the previous case was more on the semantic segmentation for the 3D models. The next part of the presentation is to use, for us, to use case the drone-based data and be able to automatically detect the thermal leaks, or what called thermal breaches and thermal anomalies, in the form of 2D representation or 2D images of the building. So in general, in energy auditing, there are 3 levels based on the ASHRAE guideline: level 1, level 2, and level 3. Infrared thermography is commonly being used in different levels of energy audit. So as we move from level 1 to level 3, we get a more complete and comprehensive assessment of the existing condition. As part of the level 3, there's a need for develop a detailed energy simulation model. And then in terms of characterization of the 3D information, as I said in the initial workflow representation, we usually want to represent thermal quantification in the form of R value and U value estimation. We also would like to represent the areas. We would be able to automatically detect the areas where we have the thermal leaks. So these thermal anomalies can be characterized in general into 2 categories of conduction-based losses as well as convection-based losses. Conduction-based losses include the geometrical thermal bridges. Convection-based losses include infiltration and exfiltration through the building envelope. You're going to see example of those. So essentially, the next part of the presentation is only focused on anomaly detection and application of automated approach to be able to automatically detect the thermal anomalies in building envelope. So here you see the application of drone-based approach in another case study. So the case study is one facade of a building called Baker Laboratory, which is located on SUNY ESF campus. So in terms of the flight path design, because we wanted to capture a high level of overlap between the images for anomaly detection purposes, we designed a rectangular flight path. We developed 2 different anomaly detection framework, of which both of them are fully automated. So the first approach is a more conventional, conventional image processing anomaly detection approach. So for this anomaly detection, the main algorithm that we use is cutting edge detection. So using the cutting edge detection, we essentially use the thermal infrared data. So the form of the thermal image is essentially a form of 2D image. So 2D image is essentially a X by Z image. And X by Z is represented by N, like X by Z number of pixels in a specific image. So the ultimate goal for application of anomaly detection is to detect the pixels in an image that represent the high level of thermal losses. So we apply dynamic threshold in order to detect the threshold that we need to characterize each segment that is showing a thermal leak or not showing a thermal leak. And then the results is being shown as a form of detected anomaly on top of the RGB image. The second algorithm, the second framework is a more novel algorithm. So it's essentially a 2-phase algorithm. So the phase 1 of the algorithm is a form of pre-processing. So in the phase 1, we apply an image segmentation. So similar to 3D semantic segmentation technique, we apply a semantic segmentation on 2D images. And the aim here is to be able to detect different domains. So for instance, here you see the mask of the window and the mask of opaque wall being represented in 2 separated images. So we first used the RGB images. We annotated a big data set about 600 images from different drone-based cases, and then use this as an input to train a unit model. So unit model here is a data-driven model, is a deep learning-based model that we use to train a semantic segmentation and be able to characterize each segment in an image and the classes that is representation of that image, that pixel in that specific image. In terms of thermal anomaly detection, this is the algorithm is based on prior research that have been already published in the probabilistic-based approach. So the main difference between this approach and previous approach in terms of thermal anomaly detection is that the detection of the thermal leak in an image is totally automated. So the detection of thermal leak in this image is based on automatic code that we developed based on a previous algorithm to detect the target threshold that we need to separate the mass of thermal anomaly. And the assumption that we use here is that in an actual image that we don't have presence of any thermal anomaly, the histogram is a unimodal distribution. However, if a thermal anomaly present in an image, we see more than one peak. And then there is a specific code that automatically finds the global maximum and the maximum between those minimum that is presented between the global maximum to find the threshold for anomaly detection. Okay. So this is an example of the software that is a Python-based software that we use to annotate the data set for model training purposes. The software called Label Me, and this is an example of how we annotate different components, different segments of an image in the Label Me software. We use different evaluation metrics that are common in computer vision and image processing to characterize the level of accuracy of the semantic segmentation. So in order to understand how much potential we would be able to get by applying a deep learning unit-based approach, we first apply more conventional semantic segmentation, including a thresholding-based and k-means clustering, and then compare the results. So this radar-based shows in terms of the characterization of all performance metrics, the deep learning outperform all other algorithms. But there is a trade-off here. So the trade-off here is that for training the unit algorithm, you need a large amount of data to be able to achieve that accuracy. These are some of the results for the characterization of the thermal anomaly for the application of the first algorithm, the more conventional approach. So you see the example of RGB image, thermal image, histogram, as well as the detected thermal anomaly. So the top image here is an example of the geometrical, the connection of the beam in wall, and then the bottom one shows another application of the material degradation. We also compare the results from the first case application with another more conventional type of data collection, which is considered manual, like FLIR thermal camera data collection. The results in terms of application of the method is almost same, but in terms of the general benefit of using a drone-based approach or drone-based thermographic approach is that using the drone-based approach to collect the thermal data, there is a huge potential for increasing the speed of data collection for large building, mid-rise and high-rise. However, for single-family residential building might not be a big difference in terms of data collection as well as anomaly detection characterization. And here, this slide, we see some of the example of application of the second anomaly detection algorithm. So the top here, we see the actual image we see the thermal image, we see the application of the histogram, which is essentially the representation of the frequency of the thermal information from different beams available in the image. And then we applied, so we wanted to understand the relative accuracy, we would be able to apply a pre-processing semantic segmentation for a specific wall domain. For instance, if you first apply semantic segmentation to separate the information. So for instance, let's say you just are interested to capture the thermal losses for window part of the building envelope, not the whole building envelope. Is there a big difference applying that over the mask of the window as well as applying the probabilistic based anomaly detection over the whole image? There is a big difference. So here you see the characterization of the histogram. Essentially, this is the threshold that was detected, and this is the result of the detected anomaly over the thermal image. And then this is the separated distribution of different domains, including wall and window. So you see a different, totally different form of the histogram, and the detected anomaly over specific domain. So this line shows the information for the segmented wall, and then anomaly detected information over the wall segment, and then the same thing for the window. For this specific example, nothing has been characterized as the anomaly for the window segment. The second example is more interesting. The reason is, so we see an example of an image that we see the presence of background information here. We see the sky. So by applying the conventional approach, we see the whole image here. The whole building has been characterized as the thermal anomaly. However, separating the window and wall using the pre-processing step, we see the two separated masks of information detected for the right side of the opaque part of the building envelope, as well as around the windows. Okay, so in terms of the characterization of average accuracy and precision, we have seen a considerable improvement. So you see for the base case, 72% for precision and recall. However, for the second algorithm where we apply the pre-processing to separate the semantic information, we have seen 92% as the average precision and 88% as a recall. So that represented a significant improvement for the state-of-the-art anomaly detection approaches. Okay. Apart from what we discussed, as part of this project, we also investigated the use case of drone-based approach for other sort of assessment. So another important assessment for retrofitting is the application of material reuse and recycling assessment. So we have seen a few studies that have been published in this area. So example of the algorithms, we didn't really dive to use the characterization of 3D reconstruction for purpose of material inventory investigation. But this is all the initial algorithm that is being used, and then the proposal of the reconstruction analytics framework that might be further explored in future studies. Okay. So we have seen example of application of drone-based approach for creating building models, as well as detecting thermal anomalies over the application of RGB as well as thermal images. In this work, we have seen the application of a new and novel method to implement a unit deep learning segmentation approach in order to improve the accuracy of the existing anomaly detection threshold-based techniques. And then we have seen a workflow that gives us the potential to create the building models to be used for the purpose of developing building energy models and for purpose of developing integrated workflows for building energy modeling. One of the things for application of deep learning and semantic segmentation, some of the techniques that we use, there is a need for a huge amount of data. And there's a need also for huge amount of data annotation. And in this regard, the quality of the data, the resolution and type of the sensor that is being used for data collection is super important. And also, for that reason, we are trying to essentially publish the data set as one of the contribution of this study. So to make it accessible to other researchers and other companies so that they can use as an input for training other and more new and novel type of algorithms for further research. In terms of the challenges for drone-based approach, some of these we have talked throughout the talk. So we already talked about the data issues, the accuracy, the sensors. In terms of the operation of the flight for collecting data, there are battery constraints. So usually for large building data capture, there is a need to consider the use case of various batteries and use one and after another for a continuous data collection. Another consideration for use case of drone is environmental conditions. So drones in general, the existing technology is really vulnerable to harsh environmental conditions. But there are further research to make this technology more durable and apply some mechatronic techniques to improve the state of the art of the stability of and durability of these systems. In terms of training and operation of the drone, there is a risk in terms of the human errors in drone operation that may cause further safety risks and issues. So considering the application of drone-based approaches for built environment, it's also important to think about and consider the training for operators and as well as the standard training approach for operation of the drone-based systems. And then the last thing is regulation. Maybe this is out of the scope of this, but that's one of the main limitations of using and implementing drone-based approach for built environment application. So for instance, right now, based on FAA rule, for any sort of research-based or commercial drone-based application, you need to get the permission from FAA. And there are structured apps that have been used by third parties that gives the drone operator to easily get those permissions. But apart from that, we have seen two examples of drone-based application. For the case of the base lab, we have done this at the Syracuse University South Campus. So Syracuse University South Campus requires any operation of the flight to further get the permission from the Office of Risk Management. So that's an example. Flying at SUNY ESF requires getting the permission from the police department from the SUNY Upstate Hospital. The reason is because the relatively small distance between the SUNY ESF campus to the hospital and the use of helicopters needs that permission in order to avoid any kind of clash or conflict between the flights. These are just two small examples, but thinking about further scaling up the application of drone in dense urban environments, for instance, application of drone in New York City to collect data. There are other regulation and specific regulation for New York City in place that the design of flight path needs to be complied with. So regulation is something to think about and consider when we are talking about the application of drone-based for building assessment and in general for built environment systems. So in general, the application of drone-based helps to scale up and reduce the speed of data collection. And in general, it helps to make the retrofit and building assessment scalable and also accessible to different communities. One of the examples of these communities are low-income and disadvantaged communities because there is significant need for them to improve the housing quality, to improve the energy efficiency in these buildings. So these techniques help to address those challenges. And then in terms of the further direction, we are expanding the study, we are collecting data, and we are trying to annotate the data and publish the data in other case studies, other building typology in New York State. And there are further opportunities to scale up this from building level to neighborhood level in order to specifically detect the retrofit target assessments and combine the role-based technique with spatial data analysis technique to propose more scalable frameworks. So that's it for today. Thanks for your attention, and we are open to any questions.
Thank you very much for a very interesting presentation. It's covered a lot of ground, right? From drone to beam to energy simulation, retrofitting. So the floor is open for questions. Yeah. Yes, Hugh, please.
Sure. Okay. Yeah. Thanks for the presentation. That's really neat. So it sounds like you've sort of figured out that you can get geometry right, and you're approaching the accuracy of LiDAR, or maybe you're there. And then you also can tell different surfaces. You can tell doors from windows. Yes. You also had mentioned R values. And so do you see any hope, so an IR camera, sort of, and we didn't talk about what it measures, but it measures surface temperature. Correct. And to do that, it makes assumptions about the physics of the surface. Do you see, so the next step is how can you predict the net R value? Do you have any hope or plans to figure that out?
Thanks for your question. This is really a great question. One of the things that we showed in the initial general comprehensive workflow that we showed was also the characterization of the R value. There are already publications and techniques that help to characterize the R value and U value using IR imaging. But the thing specifically about the application of drone is because for this specific data capture, as you said, you are just collecting data from building exterior, right? However, for R value estimation, you need at least one data point from building interior. So it could be interior building surface or could be average air temperature. So that's the minimum amount of information you need to add to this characterization to be able to characterize the average R value for the surface. But that is very important because, as you said, this work is only focused on characterizing the geometry, different classes of information, including the doors, walls, and objects in the form. But more important is to be able to characterize the existing R value, because that's one of the main performance metrics when you apply a retrofitting to be compared how much improvement was possible. And that's also another important input parameter for characterization of the existing building energy simulation software. So R value is one of the main categories in terms of framework characterization. So you really need to come up with like a scalable framework, and we see a potential. But for the sake of this project, we really didn't focus so much on quantification of R value. Our focus was something else, but there is a further potential to do further research.
Yeah, looks like there's still research needs to be done, or new technology to be developed, I think.
So I guess to follow up, I would, the indoor temperature is probably the least uncertainty I would propose. I think that knowing surface properties and is the temperature really the temperature is really a bigger challenge. So
yeah, and it's also very much the heat flux related to the weather conditions. So I think there's an opportunity to predict the heat flux and therefore the R value based on the assumption of the indoor condition, which is relatively stable, and then but fluctuating outdoors. I think there's a research going on in terms of look at dynamics, right? As the wind change, temperature change, how that image change over time. there's information that can be captured, I think.
How sun radiation affects.
Exactly. Yeah. I think that's a very rich research area and technology, associated technology development. Yes.
No, we've had discussions about this,
Yeah.
right? Understanding the emissivity of the
Exactly.
surfaces
Yes.
and what type of, opportunities exist with large data sets to be able to potentially come up with an efficient way to understand the emissivity of the surface to be able to take that next step. But not in this project. Yeah, so I just, in response to the question, said we have had discussions about potentially using large data as the source for being able to estimate emissivities to understand potential differences in the results from the thermograph.
Thank you. Other questions? Yes, yeah.
Amazing project. Congratulations. This is really hard stuff and well done. I think drones for collecting exterior data is a thing of the future, and I think it's important work. I worry that two things. One is that we're ultimately going to be limited in describing what's happening inside the building from the outside. A second concern I have is historically with energy work, when we have found some way to measure something, then attention gets diverted to that. And I'll give the blower door test. The blower door test has been fabulous to quantify infiltration, both for small buildings and for big buildings, and to diagnose where the infiltration is happening. And I have seen people, it's such a good test that people direct their attention to it. And there's less attention given to areas that are harder to do. So I worry about that. And I also worry about people's interest in remote and touchless energy audits. And we're missing some of the difficult stuff, which is inside the buildings. So long story short, any attention either by you or to others to fly through inside the building where we can count light fixtures, we can look at heating, we can look at,
Yes.
Yeah, great questions. I think there was indoor flying. There's some work on the drone measurement indoors. I think Bessie was in there. There was a faculty in, what's his name, left us? Tarek, yeah. He was flying indoors as well as outdoors, right?
Thanks.
Yeah.
So this is an amazing question. I would like to just first provide a little bit of more contextual information, because as you said, by this technology, which is more focused on the application of drone to collect data from building exterior, we would be able to collect many information from building exterior, but not so much from building interior. It's important to think about that because energy audit represent different categories of information, right? So it's important to be able to propose workflows to be able to collect data from both building exterior and interior. One of the main limitations in general is the disturbance to the occupants. So it's not easy to get indoors and collect data. That's one of the limitations in general. In particular, to answer your question, I think, Dr. Raha, that is right now at Georgia Tech, they have done a lot of also drone-based techniques, but from what I have read from their technique, is mostly also exterior-based techniques. I have a friend that was graduated from civil engineering at Stanford University. Their focus was application of drones indoors, but they didn't collect any sort of thermal or specific data for auditing purposes. And their approach was trying to propose framework to be able to make the application of drones more robust for indoor environments. In general, because of the nature of drone, it is really limited because of the risk of the collision with the indoor surfaces. But I mean, as we move forward, other researchers are doing research to try to make the control algorithms more stable. So probably we would get to the stage that we can easily apply drones in indoor spaces as well. But as of now, I haven't seen anything. I mean, reading different research that has been done in this area, nothing has been really published, because you asked specifically if we would be able to apply this technique to collect data from building interiors. I haven't seen any study that addressed that question.
Yeah, we do have faculty. I think Amit is in the mechanical and aerospace engineering, is research on autonomous drone controls that may connect with the algorithm, like developing technology for that kind of application.
So having just moved to the area, having sold a home and recently bought a home, the realtors are using the indoor drone technology to film and map the interior of residential spaces, at least. So the technology exists, the drones are there. It's just a matter of adding on those specific softwares and perhaps modules of tools to get that done.
That's great information. I think it looks like people already flying the drone, but for different purpose.
Yeah. Another thing that came into my mind about collecting data from building indoors was also the application of LiDARs integrated with iPhones. So there are softwares that is being integrated for collecting data from building indoors. Some researchers try to use those techniques to collect data. The problem with this technique is the resolution of the data is not very high, but there are still the possibility to collect some sort of point cloud data from building interiors, and then integrate those data with the exterior sources.
Yeah, actually, you reminded me, we have sponsored a project. COE has sponsored a project for a company to do the indoor scanning and look at the surface conditions. I think that's New York City. I think we can connect that. Yeah. Yes, please.
Shayan, that's a very interesting project. So at the beginning, you mentioned the buildings, right? We have commercial and residential. Is there any limit in this technology in terms of how many floors, how high it can fly, how many the square feet of the building surfaces it can survey?
That's a super interesting questions, because in terms of capturing the reality data and existing condition, one of the limitations in terms of using the laser scanning data for collecting data, there are so when you have certain height for your building, capturing data is fine. But when you get into a different, like high-rise building, you see at the higher level of the building, the quality of the capture is not that high. Also, using the laser scanning data, you wouldn't be able to capture the roof surfaces from the building. So using drone-based technology shed the light to apply this technology. And if for a specific case, there is a need for high level of accuracy, so the results from the point cloud reconstructed from drone-based approach can be combined with the laser scanner data that is characterized with a higher level of accuracy. So that's definitely a potential. Yeah.
Yeah, clear.
Thanks, James. Yeah, that was really great talk, Shayan. I'm curious about the seasonality involved in making these measurements, because one would think that, say, in the dead of winter in Syracuse, you'd have obviously a high contrast between the heat being radiated from the building and the outdoor surfaces, which would be colder. I'm just wondering, have you thought about things like how the accuracy would change and be compromised by seasonality and things like that?
Thanks for your question. This is a great question. This is a physics-based question. So yes, there are already guidelines developed for drone-based data collection in order to avoid any sort of influence on the level of accuracy from the data collection. For that reason, these guidelines, there are guidelines developed for United States and for Europe, but in general, the idea is to have at least certain level of temperature difference between indoor and outdoor when you want to characterize exterior surface temperature. Also, have relatively stable outdoor condition, for instance, semi-cloudy, when you don't have the direct presence of solar radiation that influence the surface temperature. Also something that was suggested as part of these guidelines. But in general, the answer is yes, the type of and the general quality of the outdoor environment and the difference between indoor and outdoor temperature highly influence the data capture. So that's something we should definitely take into consideration when we apply a drone-based approach for thermal data collection. Thanks. Yeah.
Excellent. I'm sure there's more questions. I would, just in the interest of time, and I think Shayan is available. Shayan and Paul will be available maybe after this to continue some discussions. Let's thank the two speakers again. Yeah, thanks.
Thank you.